All right, welcome everyone. Happy Friday if you're watching this on Friday. I hope you have a good spring break, or hope your spring break is going well if you're watching this during the week, next week. So this video, we're going to discuss or kind of go through the problem that we ended class with on Wednesday. So that problem was to maximize some utility subject to a budget constraint and some non-negativity constraints. So it was maximize my utility from beer and pizza consumption, if that's my utility. So I'm picking these two variables. And it was subject to a budget constraint. Less than or equal to some income, and non-negativity constraints. That the value of the consumptions had to be positive, but could be equal to 0. So what we had done was we set up the Lagrangian, taking our objective function minus this stuff, and we had taken first order conditions. So with respect to CB, I'm differentiating the Lagrangian with respect to CB, and then we just had 1 minus lambda 1 times PB is less than or equal to 0, and it's equal to 0 if CB is strictly positive, but a derivative could be negative if CB is equal to 0. First order condition of CP, we have 1 over 1 plus CP minus lambda 1, again less than or equal to 0, equal to 0 if CP is strictly positive. So we talked about in class that we know that from previous work that the budget constraint is going to have to bind. So I know that lambda 1 is going to be greater than or equal to 0, and I can't just simply set it equal lambda 1 equal to 0 and solve the problem. So if the budget constraint binds, we had a number of different cases. First one, which is kind of the regular one here, says that both of the consumptions are strictly positive, so the non-negativity constraint doesn't bind. So let's solve that case, right? So since both of these are strictly positive, the first order conditions are equal to 0, both of them. So I know that 1 is equal to lambda 1 times PB. I also know that 1 over 1 plus CP has to be equal to lambda 1. Since both of these first order conditions up here hold at equality, given in this case both consumptions are strictly positive. So now I can solve this for lambda 1, for example. So lambda 1 is simply 1 over PB. And so this condition over here says that 1 over 1 plus CP is equal to lambda 1 equals 1 over PB. So 1 over 1 plus CP is equal to 1 over PB. Now if you look at that, that is exactly the margin utility of pizza consumption over the margin utility of beer consumption times, or equal to, the price of pizza, which is 1, divided by the price of beer, which is PB. So notice we still get margin utility pizza consumption over margin utility of beer equal to the price of pizza over the price of beer. It's just that in the way I set up the problem, the price of pizza is simply equal to 1. So PB is sort of the relative price. And we arrive at that same kind of basic condition when I have strictly positive consumptions. So I can solve this equation pretty easily for here, for CP. So I can flip both of those, and I just have 1 plus CP must be equal to PB. And so CP is equal to PB minus 1. All right, now we can already note, because this will help, right? When is this case going to be true? Well, when is CP positive? Right? That was our assumption. And so I need to make sure that it's possible for that to be true in this case. And here we can see that, yeah, that's absolutely possible, provided that PB is greater than 1. And, right away, I mean, we have to get a feel for the rest of the problem, but there's some intuition there, right? PB is the price of beer relative to the price of pizza. Price of pizza being 1, right? So in other words, if the price of beer is greater than the price of pizza, well, then my consumption of pizza is going to be strictly greater than 0. I don't want to set pizza consumption equal to 0 because pizza is the cheaper good here. So I'm going to tend to move towards pizza consumption. So there's already a little bit of intuition there, right? I'm going to consume pizza as long as beer is expensive enough relative to pizza. And that's what we found there. Okay, so now what is consumption of beer in this case, right? So here I can use the budget constraint, So remember my budget then, which is coming from my complementary slackness condition, says that PBCB plus CP has to be equal to I. We know the budget constraint is going to bind. And so I can plug in for CP here. Get that PB times CB plus PB. Oh, my pencil is malfunctioning here. Plus PB minus 1, that's CP, has to be equal to I. So PB, CB has to equal I plus 1 minus PB. And then I can divide by the PB. And I get this for CB. And again, right, so we have to make sure, is that going to be positive? And we see that, yeah, this can definitely be strictly positive, provided here, in this case, that PB is not too large, right? Or too small, I guess. So let's see here. So when is CB strictly positive? Well, that would require this number to be positive. And so I can, solve that out. It has to be greater than 1. And so I plus 1 has to be greater than PB. Or, another way to put that is my income has to be greater than, PB minus 1. So again, I've got kind of some conditions on where PB needs to be in order for my consumptions to both be positive, right? So remember what we had before, that CP is positive when PB is bigger than 1. So if I kind of take this and combine those, I would have both of these strictly positive if PB is in a certain range. So as long as PB is high enough that I still want to consume some pizza, but not so high that I can't afford to eat stuff higher than my income, then I'm going to consume positive amounts of both beer and pizza. And so we can kind of see it makes a lot of sense, right? Like, which case am I going to get to is really ultimately going to depend on how big or high the relative price of beer is compared to my income. Okay, so we solved this case. I have, if you gave me income and prices, I can tell you exactly what my beer consumption is and exactly what my pizza consumption is. And so this case can definitely work, and it's one possibility. So the second case, we have two more to handle, is one positive and one is equal to 0. So let's just start, say CB is 0, but CP is strictly positive. So now the first order condition for pizza, well, first order condition for beer is less than or equal to 0. So I have, was 1 minus lambda 1 times PB. It's less than or equal to 0. So the only thing that really does is it basically rules out using that first order condition to solve for anything, right? I can't solve that for lambda 1 because it might not be equal to 0. The other constraint, the other first order condition, 1 over 1 plus CP minus lambda 1, that does have to be equal to 0 because in this case, CP is strictly positive. Okay, so that one, you know, I could solve for lambda 1 and I would know the value of the multiplier as we get there. Now, so I mean this, when we get to the end, if we care about the multiplier, which we might, we know what lambda 1 is. But how do I actually find CP, right? I can't plug this back into the other first order condition here because I don't know it's equal to 0. But what we do know is we already know what CB is. CB is 0 in this case. So the budget constraint will tell me what CP is. If that is 0, well, CP is simply equal to I, right? So we're okay there, right? So as long as these conditions are true right now, or unless under these assumptions, CB would be equal to 0 and CP would be equal to I. Now, how do I know when this case obtains or not? Well, we kind of had a hint in the first one, right? So those cases sort of tell me when would C be equal to 0? Well, that's going to happen if this condition here fails, right? If PB were less than I plus 1, or sorry, greater than I plus 1, then I might run into problems. So let's see if that comes out again, right? So what would I do? Well, I can take lambda 1 here, and I can put it into this. And so I can say 1 minus 1 over 1 plus CP times PB is less than or equal to 0. But I know in this case that CP is I. So I have 1 minus 1 over 1 plus I times PB less than or equal to 0. Now I'm going to move things around. Now anytime you're working with an inequality constraint, you have to be really careful, ensure that if you're going to multiply by something, you have to know that it's positive. So we're good here. Everything is positive, so I can manipulate this inequality constraint and not run into problems. But you always want to be careful. It's easy to multiply something across that's negative or potentially 0, and your inequality is going to be incorrect. Okay, so this says that 1 is to be less than or equal to PB over 1 plus I, if I just add that over. And then if I multiply both sides by 1 plus I have 1 plus I less than or equal to PB. And so that's exactly what we had before, right? So when would CB be equal to 0 is if the price of beer is too high. If the price of beer, relative price of beer, is more than I plus 1, I am not going to consume any beer. I'm going to consume all of my income on pizza. All right. So everything is checking out so far. So after it's hard to follow in real time, but when you go back and look at this and look at my notes here, then I post them, you'll see, okay, these conditions are all checking out and providing the same results. So our last case is I consume beer but no pizza. right? So liquid dinner here. So in this case, this constraint has to be equal to 0, but this one does not. This is because CP is strictly positive, and in this one, CP is 0, so I don't know if that first order condition is 0 or negative. All right, but again, I can just use the budget constraint. All right, if I don't consume pizza, very simple calculation to find my beer consumption. Beer consumption is income divided by whatever the price of beer is. So then, let's check, right? When would CP be equal to 0? Well, I can kind of take my first order conditions, right? So I know that 1 is equal to lambda 1 times PB, so that lambda 1 is 1 over PB. And what we kind of already reasoned out before, we've already done this basically, but I'll review it again, is that 1 over 1 plus CP, which is 0 in this case, has to be less than or equal to lambda 1, which is 1 over PB. If we did that all correctly, and since CP is 0 in this case, I just have 1 less than or equal to 1 over PB, or another way to say that PB is to be less than or equal to 1. That's exactly opposite what we found in part A when CP is positive as long as PB is greater than or equal to 1, right? So this case is certainly possible, right? If beer is relatively cheap compared to pizza, I'm going to go for beer, right? And so in this case, we've characterized all of the possibilities, and they make pretty good sense, right? So if we kind of summarize these, so let's see, what were our exact conditions here? If PB is in this range, I think it was just I plus 1, right? Yeah, that was what we had. Then both of these are positive, and we know exactly what the solutions are for consumption. And then if either one of those goes the other way, one of those consumptions is going to be set to 0. So if the price of beer gets too expensive, if this other one is violated, so PB becomes greater than or equal to I plus 1, well, too expensive, no beer, I'm going to spend all of my income on pizza. If beer is quite cheap relative to pizza, then I say, you know what? I don't want any pizza. I want only beer. And that tells me exactly how much beer I'm going to consume. So with quasi-linear utility, my Anata condition is not satisfied, which means I'm going to tend to go potentially to one of the corners, right? And whether or not I go to 0 consumption in either of the two goods just depends on how expensive they are relative to each other. And we've characterized that with PB. So if I gave you an example with numbers, you could look at these conditions and take the income and the price, and you could know exactly which case is going to obtain. And so maybe I'll put up a problem like that where you don't have to resolve it. You can use these conditions and then potentially, ex post see what is going to be true. So there you go. Fairly, I don't want to say straightforward. There's a lot involved in this problem, but nothing too tricky, right? It's just a matter of taking the first order conditions of the Lagrangian, like we've always done, and then just keeping track of all the different cases and possibilities. And so there we go. So hopefully this gave you some insight into this problem. and you didn't find it too bad, and we'll get some more practice with these non-negativity constraints.